Welcome to a little demo video showing you how to get in touch with YASARA on Windows 8 tablets. We'll have a look at the user interface, molecular graphics, interactive molecular dynamics simulations, and finally some docking. This little notebook is Samsung's Smart PC 500T. It comes with a 2GB RAM, a solid-state disk and an Intel Clover Trail chip, which includes 2 Atom CPU cores that are doubled to 4 thanks to hyper-threading and a Power VR GPU for the graphics. So this system is clearly not optimized for performance but for mobility. You can expect up to 12 hours battery life. When you run YASARA for the first time, just right-click on its icon to pin it to the taskbar. The screen is actually a touchscreen and, even better, when you need more mobility than this tiny notebook can offer, just push the button. You lose half of the battery life, but gain a tablet that weighs around 700 grams. So the computer is actually behind the screen and not below the keyboard. The very first step is to enable YASARA's virtual keyboard, which, as a side effect, puts YASARA's user interface into touch mode. In touch mode, the interface is fuzzy. It's enough to just tap somewhere nearby to activate an option. And the interface is zoomable to make sure that the size of the widget matches the size of your fingers exactly. At Options, Input Devices, Virtual Keyboard Parameters, I can configure the virtual keyboard, changing its size and transparency. And most importantly, don't forget to choose your favorite keyboard layout. Over 60 are available. To show the virtual keyboard, tap on the left side. The keys have exactly the same functions as on a real keyboard, so everything is where you expect it. For example, the function keys F1 to F8 change the scene style. You can work with YASARA normally while the keyboard is visible. To make it disappear, just press the hide key up here. If you already know in advance that you only want to press a single key, tap on the right side. Then the keyboard will disappear again right afterwards. Now let's look at the gestures. Hold down a single finger to rotate around the X and Y axes. Of course, you can spin. If you now add a second finger, you can also translate along the X and Y axes. Alternatively, if you tap and hold 2 fingers at the same time, you can use the famous pinch gesture to translate along all 3 axes and rotate around the Z axis. If you now add a third finger, this finger rotates around the X and Y axes. So with 3 fingers, you got access to all 6 degrees of freedom. A short tap on an atom marks it. If you hold down the finger without moving it, you enter the context menu, for example to color the residue. And now a little trick. Even if the virtual keyboard is hidden, the bottom key row is active. For example, I can hold down the Control key and tap on additional atoms to measure distances, angles and dihedrals. Or I can hold down the Alt key to repeat the last command, coloring residues in this case. Or I can press the Space key to enter the command console where analysis results are shown. Now, just for fun, let's stress the hardware a bit. I load PDB file 1AON, the chaperonine GROW ELES, a giant protein with about 60,000 heavy atoms. And you can see that even in space-filling mode, YASARA's highly optimized graphics engine reaches interactive frame rates, including shadows calculated in real time. Same in balls and sticks modes. The features you have seen so far are part of the free YASARA View program. If you own YASARA Structure, you can do much more than that, for example, docking, which I'll show you next. I load PDB file 4F7V, which is the X-ray structure of E. coli HPPK, a pyrophosphokinases in the folate biosynthesis pathway. The enzyme transfers a pyrophosphate from ATP to hydroxymethyl dihydropterine, which makes it an attractive drug target. The crystal structure already has an inhibitor bound, which is a bisubstrate analog, so one half looks like ATP and the other half like dihydropterine. Let's see if we can dock this inhibitor. Of course, it shouldn't be too easy, so we don't want to do bound docking, where receptor side chains and ligand are already in the right conformation. Instead, I randomize the structures a bit first, which is a good opportunity to show you how interactive simulations work in YASARA. I delete the water molecules and split the object in two, so that receptor and ligand can be handled separately. A bit later, I'll need a selection of active site residues. For simplicity, I already create it now by selecting those residues that have a side chain close to the ligand. The ligand's residue name is J1D, so I choose to select residues and type side chain with distance smaller than 3.5 from J1D. I'll use this selection later. I clean the structure for simulation by adding missing hydrogens and so on. Let's randomize the receptor side chains, but not the backbone, so I need to fix the backbone. Then I choose the Nova force field, which has been optimized for quick calculations without explicit solvent. Finally, I select a steepest descent minimization and start the simulation. YASARA now automatically derives force field parameters for the ligand using the general amber force field and AM1 BCC charges, which also work with the Nova force field. Now I switch from minimization to MD to start the randomization. I also check the temperature, which is 298 Kelvin, and while this is in progress, I pull the ligand off the receptor. So I mark one atom in the ligand, then I hold down the control key and pull the entire ligand object with 2 fingers. Here it goes. Enough. I switch to simulated annealing energy minimization to remove all the kinetic energy I just pumped into the system. And I stop the simulation. To keep track of what I'm doing, I now save the structures to disk. First, the ligand. I choose the file name 4F7V_ligand. And second, the receptor, so I can get rid of the ligand. Actually, let's restrict the search space first. I unselect the backbone atoms. Then I create a docking cell around the active site, which I already selected previously. So I choose to extend the simulation cell 5A around selected atoms. Then I fix all atoms except the selected side chains in the active site. These are the ones that will be kept flexible during docking. Now I don't need the selection any longer. And I save the entire scene, which is the receptor and the docking cell. I choose the file name 4F7V_receptor. Docking is handled by a macro, so I need to choose a target the macro can work on, which is simply the common path to the files I just saved. And finally I start the docking. YASARA now runs the VINA docking program, a great tool developed at Scripps Research Institute that can be conveniently distributed together with YASARA thanks to its open source license. The classic autodock is also included, by the way. VINA now does 25 docking runs. This takes some time, so I'll do a fast forward with the magic remote control. And here we are back. Due to the many flexible side chains, this docking run took quite a bit, so it's something you want to start in the evening with a power plug connected and then check the next day. Time to start the docking result player, which is just another macro, and see what we got. Yes, luckily, the complex with the best energy looks very much like the crystal structure. The ligand heavy atom RMSD is 2.8 angstrom. Many thanks for watching. Don't hesitate to get your personal YASARA from www.yasara.org. And don't miss the many other help movies, especially those in YASARA's help menu.